All right, let's move into chapter 26, which is officially called Current and Resistance. So current is a little I. We talked about this way back in like chapter 21. We briefly said it. Your book calls it a little I. The lab manual and a lot of other things are going to call it capital I. But again, we generally in the book have this be little I. Why are you not letting me do this? Officially, it's the rate of charge flow. So dq dt over past a little region has units of from the current over time, or sorry, charge over time. So we have coulombs per second, which is officially an amp. In physics, we have a thing called conventional current, where we pretend that it's the positive charges that are flowing in an electrical current circuit. I'm sure the book talks about conventional current somewhere in here, and you can talk about, you can read their validation of why that's true. It doesn't. This is almost one of those situations where we have two wrongs make a right. Anytime you would go through and actually have the negative charge be the one that you were talking about moving, you'd end up making another correction or a correction or a calculation which would change everything around, so it doesn't actually make a difference that we say that the positive charges are things that are flowing. But what that really means in terms of when we're doing these circuits is that when we're drawing the direction of our current, which we will do, we're going to have it flow from the positive terminals to the negative terminals. We're going to pretend like current is coming out away from the positive terminal, like a positive charge would want to do. And it was going to move in this situation here, it's moving towards the negative terminal. So our direction of current flow is going to be like a positive charge is moving. All right, the other title in the name of the title of this is resistance. This is this capital R, and it's actually referring to the resistance of an object or the element, the circuit element, to electrical current. So some things have more resistance than others to allowing current to flow through them. Essentially, this measures how good a conductor something would be. And the actual equation for something's resistance is the voltage drop across that element or object divided by the current which is flowing through the object. So this V, again, is the voltage drop across our circuit element, and the little I is the current through that circuit element. So resistor, something will have current go through it, and that it has a voltage drop across it. These prepositions are really important here. So voltage drop across, current through. Because of what we're talking about here, we end up with units of a volt over an amp. That's officially an ohm. It's the capital omega, Greek letter omega there, but it's officially called an ohm. Some objects, some circuit elements have a set resistance. No matter what the electric potential is, whatever the voltage drop is that's across it, it always has the same amount of resistance. We call this an actual resistor. Some things have a variable resistance. In other words, it changes how resistant they are depending on how much current or whatever is flowing through it. But a resistor has a set resistance, at least for a large range of voltage drops across it. So a resistor also has a symbol. It looks like this. Again, it's like a squiggly line. Resistors obey what we call Ohm's law, which says that the voltage drop across it is the current through it times that set resistance that it has. And we'll use resistors in lab. Wednesday's lab already done that, and then tomorrow night or Monday night this week we'll do it. And again, we'll have a couple more labs where we'll use resistors in our lab. We can make a resistor, this is how you make resistors, using this equation where this rho is the resistivity of the material that you're making your resistor out of. The L is the length of the resistor, and the A is the cross-sectional area. You can also have a sigma, which is the conductivity of the material, which is just 1 over the resistivity. So if you have a large resistivity, you have a very small conductivity, or vice versa. If you have a very small resistivity, you'd have a large conductivity. They're inverse to each other. So number 17 says we're going to have a wire made of nickel, chromium, iron alloy. Goodness, yes. And it's going to be 1 meter long. So our L is this 1 meter, and the cross-sectional area is 1 square millimeter. We're going to have, so again, our R then would be rho L over A. And then it tells us that there's going to have a current of 4 amps when we have a potential difference, a voltage drop of 2 volts. And we remember that V equals I times R. We're making a resistor. And so R is rho L over A. So we'll put everything in here. We'll say, okay, 2 volts is 4 amps times rho. 1 meter is our length. Now, I need to convert this into meters as well. But I need it to be meters squared because I have millimeters squared. And so 1 meter has 1,000 millimeters in it. And so 1 square millimeter, I actually take that 1 and I divide it by 1,000 squared. So this is 1.0 times 10 to the negative 6 meters squared. And I can get rho from that. Let me come back. All right, so when I do that calculation, I get the resistivity is 5.0 times 10 to the negative 7 ohm meters. But that means that the conductivity, which is actually what it wants me to find out, which is 1 over rho, is, oh goodness, why is this not in scientific notation? 2 times 10 to the 6. And that is in 1 over ohm meters. Yeah, so that's our way that we can calculate the resistance of some sort of material. Another thing we should talk about is the power that's delivered to a circuit element per second. So our unit of time. So the power that any particular circuit element receives, which is the energy that's per time, the energy per time, is the current, again, that goes through it times the voltage drop across it. So any particular circuit element is going to have some sort of current that flows through it, and it'll also have some sort of voltage drop which is across it. And so this current times voltage is the power. If you have a resistor which obeys Ohm's law, then you can also do the power, either you can do it in terms of current or you can do it in terms of voltage drop. So number 41, we do this type of calculation. It says that we have a potential difference, which is our V. The potential difference across our space heater is 120 volts, and its resistance is 14 ohms. And so we want to know what's the part A, what's the rate that energy is transferred to it in thermal. That's basically the P. So we can either do IV, or we can do, again, here we'd rather do V squared over R because we know V and we know R. So 120 volts squared over 14 ohms. 120 squared divided by 14 is 1,000. I'm going to say 30. Now this is a joule per second, right? Energy per second. Officially, this is a watt, right? A watt. But that's our rate of energy transfer. For part B, it says if the cost is this per kilowatt hours, 5 cents per kilowatt hour, how much would it cost if we ran this for 5 hours? So the cost per kilowatt hour, this is an actual unit, is 5 cents. That's what this is trying to say. So let's see if we can't figure it out. If we run the heater for 5 hours, oh goodness, I'm running out of space here. Then the amount of energy I'm using, or the kilowatt hours, I would basically, this is 1.030 kilowatts. So 1.030 kilowatts times 5 hours is 5.15 kilowatt hours. And each one of these is 5 cents. So 5.15 kilowatt hours times 0.05 cents per kilowatt hour means that I need to pay 0.2, say 6 cents, 26 cents to run it. It's actually a pretty good deal for a space heater. One more thing I want to talk about in this chapter is another, instead of talking about voltage source. So I said that I wasn't going to use the VS symbol. So instead of that, we're going to talk about EMF devices. So an EMF device is a source of direct current. EMF is an old term. EMF stands for electromotive force, which is what people thought was happening when you connected wires or something up in a circuit, is that somehow there was a force, right, causing things to move. But what they were rating, what they were actually measuring, is not actually the force, which is the electrostatic force. It's something else. It's actually the electric potential, or electric potential difference. So it's an old term. Again, it's capital epsilon is the actual symbol for it, and it's really the work done for each little DQ. It has units of voltage, and so an EMF device is just a voltage source like a battery or a DC power supply, but we're going to use this symbol, EMF, instead of VS, instead of voltage source. We're going to use EMF because it's more general, and it doesn't always have to be a battery or a DC power supply. It turns out things like magnetic fields themselves can produce an EMF. They can produce a voltage source. And so rather than writing it as a VS, we're going to use the more general symbol, which is EMF. And so I'm going to have an epsilon next to my batteries and DC power supplies instead of V's during our class periods. And again, so here's an example of, say, a circuit diagram where instead of having a voltage source, I'm going to say, here's my EMF, And again, the symbol looks just like what we had for a battery. I have a resistor 1 and a resistor 2 and maybe a capacitor. This is a series circuit diagram with an EMF, 2 resistors, and a capacitor. Maybe while I'm here, I will go ahead and introduce our 2 rules. So this is officially chapter 27. You know what? I'm not going to. I'm going to leave it for the next one so it can be distinguished. So that's all really for chapter 26. And we'll move into chapter 27.